Once you feel comfortable with the concepts of parameterized surfaces, we can now do very nice things with these concepts, such as specifying curves in the surface, calculating tangent vectors, and calculating normal vector. And these are beautiful things that we can do with the expression of the parameterized surface, and which I'm showing all of them together here, but which I would like to walk you through it. So our starting point is some parameterized surface R of uv. Okay, so you know that R of uv is a function, three functions, x of uv, y of uv, z of uv, which define this surface. Okay, and you know that we can now draw a grid in this surface corresponding to different values of u and different values of v. So let's say, for example, that here I have u, the u is increasing, let's say, from u equals 0 here, u equals 1, and here u equals 2. Okay, so as we increase u, we are moving in this direction, yeah, which is what I indicate by this arrow here that says u. And then when we change different values of v, so let's say that here we have v equals 0, here we have v equals 1, and here we have v equals 2. So these are these lines of constant v. So by increasing the parameter v, we are moving along the surface in this direction by increasing the parameter v. Okay, so this means that the two parameters define different directions in which we can move along the surface. Okay, but now this is great, because what if we want to find the equation for individual curves, such as this curve here, which is highlighted in blue. Okay, so this is a curve in three-dimensional space, and this curve corresponds to the equation of RUV, but substituting v equals 1. Okay, so let me write that down. This is curve with constant v. And that's what I wrote here, R of u and v0, which is a constant value. Okay, let's do an example of that. So let's imagine that our surface R of uv, I'm going to make this up on the fly. So let's say it's this equation, 1 plus u times v, u squared plus v, and let's say 2 minus u plus v. Okay, so this is our parameterized surface. So now if we fix v equals 1, r of u comma 1, this would be an equation that would, by substituting v equals 1, I get 1 plus u, then I get u squared plus 1, and 2 plus 1, so 3 minus u. Okay, so I get this, which is now a function that depends only on u. This is the parametric equation of a curve in 3D space. We will see a lot about parametric equations of curves in the chapter 4.3, integration line integrals. Okay, but for now, remember that if you have 2 degrees of freedom, you define a surface. If you have only 1 degree of freedom, we have only one parameter. We can only move in one direction. So this defines these lines of constant u or v. Okay, so this is when we fix v to be constant, but we could also define a line, a curve, with constant u. Okay, which would be lines in this other direction, like this line highlighted in red. Okay, excellent. So that's the concept of curves in the surface. Now we can define tangent vectors to the surface. Thanks to the fact that we can define curves in the surface, we can also define tangent vectors. Do you remember that when you had a curve defined by a vector that depends on a variable, for example, time, do you remember that you could calculate the velocity, which is also a function of time, by doing the partial derivative or the derivative of r with respect to t? So this gives you, whenever you have a curve that depends on one parameter, doing the derivative with respect to the parameter gives you a vector tangent to the curve. Okay, so this is a property of vectors that depend on one parameter when you do the derivative. So this means that if we calculate the tangent to the curves of constant v, like this blue curve here, if you calculate the derivative of that with respect to u, you will get this arrow here, okay? While if you calculate the derivative of this curve, which has a constant u, yeah, u equals 1, if you calculate the derivative of this curve with respect to v, you will get a tangent vector to this curve, which is this red arrow here, this red vector here, okay? So this is what we call the tangent vectors. So the way we can do it is, if we want to create a vector that is pointing in the direction of increasing u, we have to do this vector we can call tau of u. So this is the partial derivative of r with respect to u, okay? Why partial derivative? Because when we write partial derivative, we are automatically assuming that v is constant, okay? So that's exactly what we're saying. We are keeping v constant, for example, v equals 1, and then we're doing the partial derivative with respect to u. And since u is increasing in this direction, we get this vector, this tangent vector, this blue vector here, okay? So that will be tau of u. Similarly, tau of v, which is a tangent vector to the lines of constant u, that will be the partial derivative of r with respect to v. And that will give you a vector pointing in the direction in which v is increasing. So remember, v was increasing in this direction. So if we fix a curve with constant u and we calculate the partial of r with respect to v, we get this vector here, tangent to that curve. Okay, so we get two vectors that are tangent to that curve. Not only are they tangent to that curve, but the length of these vectors tell us about the rate of change, right? Remember that if you do the derivative of position with respect to time, you get the velocity. So the direction of the velocity is tangent to the curve, followed by the position, but also the length of this vector tells us how fast we are moving. So how fast is the position changing when we change the parameter? And that's exactly what the length of this vector is telling us. So if v equals 1 is this line here, and v equals 2 is this line here, so it's clear that when we increase v by an amount 1, we change in this direction by approximately this distance, right? So this distance is telling us about also the speed by which we are moving through this curve, okay? So those are the tangent vectors, and we can do an example following the example here. Let me move the examples to the right. Example. So we started with a parameterized surface. R of uv. Then we can calculate curves along surface, which just represent R of u0v or R of uv0, which represent keeping one of the two parameters constant. And that's an example of what we did here. And now we can calculate tangent vectors. And the way we do it is we get our original surface and we do the partial derivatives with respect to the two parameters, okay? So if we do the partial derivative of this with respect to u, we are going to get partial of r with respect to u is equal to 1 plus v. Remember, we assume, sorry, not 1, we get 0 plus v, so that's v. Then the partial derivative of this with respect to u will be 2u plus 0, so 2u. And then the partial derivative of this with respect to u will be 0 minus 1 plus 0, so it will be minus 1. Okay, so now this is the expression for a tangent vector to the curves of constant v, because the partial derivative with respect to u is assuming that we have kept v constant, okay? Then we can also calculate, of course, the partial derivative of r with respect to v. And doing that, we get u, 1, and 1. Okay, so that will be a curve of tangent to the curves of constant u, such as the vectors drawn here. Now finally we are ready to calculate a vector that is normal to the parametric surface. So this vector always points away from the surface, and it's exactly at 90 degrees with respect to the surface, always, at every point, okay? And the way we do that is very easy. If we have two vectors that are tangent, how do you find a vector that is normal to both? you just do the cross product. Okay, so normal vector, and this is really important, is n, we call it capital N. This is equal to the cross product of the two tangent vectors. Okay, cross product of the two tangent vectors. For example, here, in this example here, where we had this surface, we calculated the two tangent vectors, and remember that these two tangent vectors depend on u and v, of course. Yeah, so this is a vector tau u that depends on u and v, and this is a vector tau v that depends on u and v, because depending on where we are on the surface, the tangent vectors are different, of course. So now the normal vector will also depend on u and v, so we have to do the cross product of tau u cross tau v, which is the cross product of v 2u minus 1 cross u 1 and 1. And you remember how to do a cross product. We write this determinant. And therefore this is x hat times this determinant here minus y hat times this determinant here plus z hat times this determinant here. So this is u plus z hat times v minus 2u squared. I'm sorry that I ran out of space, but you can see that we have gotten a normal vector n which depends on u and v. Okay, just by doing a cross product of the two tangent vectors. Maybe I would prefer to write this as the partials. So it's more consistent. Okay, so that's how you can find, starting from the equation of the parameterized surface, we can find curves with constant v or constant u. We can find the tangent vectors, and we can find the normal vectors. Okay, and this normal vector depends on u and v. So at each point on the surface, we will have to draw a different normal vector, right? So depending on where we are, the normal direction will be different. Yeah, so that's why our vector n depends on u and v. Okay, let me rewrite this because I don't like how I wrote it. If I delete that intermediate step so that I can move this up, I now have space to write this as a vector. So this is our vector n, which for every value of u and v has a different, it's a different vector. Okay? Very well. So I hope these concepts were clear, and you now know how to calculate tangent vectors and normal vectors to any surface that I give you. Excellent. See you in the next video.